All right, so the clique or the clique of the graph is your complete subgraph on your graph. The maximum clique or clique is the one that's got the most number of vertices. And remember, we've talked about this before, the size of the graph is the number of edges, the order of the graph is the number of vertices, so max order there is maximum number of vertices, and the symbol of the omega W is that number of vertices in your maximal complete subgraph. All right, now, when we look at these things, no, it froze on me. Oh dear, that of course happens. All right, so when we look at these things, we're looking at the, oh, I shouldn't have said size there. I really should say, it can be called size. They often are called size, but it's technically the order because it's the number of edges here. So when you talk about cliques, you can refer to them in the following way. So you've got the one clique or clique. So for this guy, that's exactly referring to a subgraph that's the same as K1. Now, if you remember what the complete graph on K1 is, that is just a bunch of vertices. So what does this tell you? This tells you that pretty much what? Every single graph that we see, unless it's the one graph that you literally do nothing with because there's no vertices, no edges, pretty much every graph is going to have a one clique or a one clique because it has vertices. Now, if you look at a two clique or a two clique, this corresponds to a subgraph that is isomorphic to K2, or the complete graph on two vertices, and this is literally corresponding to you have edges in your graph. So as long as you have a graph that has vertices and edges, which, let's face it, most of them do, not all of them, but most of them have at least one vertex and at least one edge, so really at least two vertices and at least one edge, you're for sure going to have a one clique and a two clique, okay? Now, what would a three clique look like? Anybody have a guess? Yep. So this guy is isomorphic to K3, or this is where you are looking for something that looks like a triangle. And let me actually just draw it because, hey, we're a graph class. We can draw things. So you're looking for something like this. In other words, you're looking for triangles in the graph. Okay? Now, a couple of things to remember, actually, before I get into that example. A couple of things to remember, and this is stuff that we've done previously with graphs. So recall, and this is information about your complete graphs. Okay, first of all, it has what? The number of vertices is n. So if you're looking for a clique or a clique in your graph, what happens? If you're looking for say a 5 clique, which we haven't actually written out yet, you'd be looking for 5 vertices. Now, one of the ways that you actually spot which, say, 5 vertices that you want to find is you look at the degrees. When you're in a complete graph, the degree of every vertex is exactly the same, and every vertex has to be adjacent to every other vertex in that complete graph. So that, remember, means that the degree is n minus 1. And that, I have to admit, I find is one of the best ways or one of the easier ways to find your cliques in your graphs. Okay? And so, for example, if we have a 4 clique, this is the first one where it actually gets a little bit harder to find. And as soon as you get to 4 or more for your n cliques, this is where that strategy really comes into play. So you're looking for a complete graph on 4 vertices, and remember, this guy can look in all sorts of different ways, which is one of the reasons they're harder to find. One of the ways is you're looking for a square or a box with 2 lines crossing in the middle. Okay? But remember, that's not the only orientation that can look like. The other way that it can look like was, and we saw this earlier, it can look like a big triangle with a vertex in the middle. One of the things that you might not have noticed previously, but actually is a thing, notice here the previous clique or the previous complete graph, K3, looks like a triangle, is actually inside of or is a subgraph of of the for the complete graph and 4 vertices. It's a thing that happens. All right, so let us apply what we know with respect to this guy. All right, so look at this graph right here. We see a graph that has 6 vertices. Definitely easiest to count up your 6 vertices when they're numbered with actual numbers as opposed to letters like we often have. And I put them, roughly speaking, in a circular fashion. So you've got edges crisscrossing in the middle and edges around the outside, but no edge here between 5 and 6. So the question here is we want to know what is the maximum clique or the maximum clique in this graph, okay? So let me title what we're about to do. So we want to find the maximum clique. And I go back and forth because I learned this stuff from somebody who was European, and they say clique in Europe, and they say clique over in the U.S. most frequently. So you'll see me go back and forth there. Yeah, so I'm going to do this progressively. But yes, that is a strategy in terms of how to start thinking about it for those of you who started sending guesses. So if we look at K1, in other words, a 1 clique, for sure we have it because we've got vertices. K2, you look to see if you have edges. So here for 2 cliques, we definitely have multiple 2 cliques because we have edges. So the first one that actually takes any work whatsoever is K3, and that's where you spot triangles. And as a couple of you noticed, yes, there's multiple triangles. There's actually a bunch of triangles. In fact, I would say any 3 vertices is a triangle, but we don't have quite that many lines. So here, 2, 3, 4 is a really easy one to spot. What did you guys send in? 3, 4, 6 is also a one to find. So yep, we've got triangles too. Okay. Now, then you start looking for K4, and it looks like a couple of you guys found K4, but let me go ahead and highlight this so it's easier to see together. You guys said 2, 3, 4, and 5. 1, 2. So I see 2 guesses. It looks like only 2 different guesses for the 4 clique or the complete subgraph on 4 vertices. 1, 2, 3, 4 isn't going to work because we don't have the edge between 1 and 3. But let's check the other one. I think that one may work. So we have 2, 3, 4, 5. Is that the one you guys sent in? Yeah. So yes, here what happens, remember, you need to have it where every single vertex in the subgraph touches or is adjacent to everybody else. So 2 is adjacent to 3, 2 is adjacent to 4, 2 is adjacent to 5, so we're good there. 3 is adjacent to 2, got it. 3 is adjacent to 4, is adjacent to 5, so we're good there. Now 4 is adjacent to 2 and 3, done, and 4 is adjacent to 5, and 5 is adjacent to the other 3. In other words, in these highlighted edges, notice it looks like kind of a square-ish shape and 2 crosses right there. Now notice there are other edges going in and connecting to these 4 vertices, but what we're looking at is simply a subgraph, okay? So I'm going to go ahead and write this one down. Whoops, not meaning to do that. And then yes to your other question. So this one is yes, C, 2, 3, 4, 5, the vertices. Okay. Now, if you want the maximum clique or the maximum clique, you have to check all these different complete subgraphs. And the check. So this guy is K5. I'm going to let you guys look for it for a couple of seconds. Okay. So remember, K5 means you have to have 5 vertices. So you've got 6 vertices here. So you're looking for what? You are looking to see if you can use all the vertices, save 1, and get a copy of K5. So let you guys look at for a second and see if you get a guess of, do we have a 5 clique in here or not? All right, I've got several guesses. So while you guys were making your guesses, I was making little notes there at the bottom, which was moving on to the next one, which was checking to see if there was a 6 clique. Okay. So here, it turns out your complete subgraphs are always nested. So the first time you don't have one, you're not going to have any of the bigger ones either. But notice how we're on 6 vertices. The maximum clique that you could ever possibly get is K, and then the subscript is the number of vertices in the graph. Notice, though, this graph is not a complete graph itself, because we're missing an edge here between 5 and 6, 1 and 5, 2 and 6, etc. So since the graph itself is not a complete graph, there's no way you're going to get a 6 clique in this particular graph. Okay? Which means the question is, do we have a 4 clique or a 5 clique as our maximum clique? Now, what you guys were saying in your analysis is the correct way of finding out if a clique doesn't exist. And this is one of the reasons why up here, and let me highlight it for us, I went ahead and said, hey, remember what's going on in your complete graphs. Your complete graphs have the n vertices in the subscript, no worries. That part's explicitly given to you if you write it as k with a subscript, or if you just write it as 1 dash clique. The number in the subscript or the number in front of the dash tells you how many vertices you're looking for. The big thing that you're really looking for is you need to have that all of the vertices in that set of n vertices that you're checking have to have at least degree n minus 1. So let me throw that to an example in K4, and then we'll bump it up to the K5. So K4, there was a bunch of different possibilities here in terms of 4 vertices. I mean, you had, what, 6 different choices of picking 4 vertices. These guys here, the degree of vertex 2 is degree 4. That's bigger than 3. The degree of vertex 3 is also 4. That's bigger than 3. The degree of vertex 4 is also, is 5. That's bigger than 3. And the degree of vertex 5 is 3, which is at least as big as 3. So we're good there. So that then is just checking to see if all the edges actually join where they're supposed to. But if you take something like this guy right here, like 1, 6, 2, 3, notice this one has degree 3, degree 3, degree 4, degree 4. So those are also 3 or bigger, so that's a possibility. But these edges that were degree 3, they've got some edges that don't go back to 2 and 3, so that's not going to work. If you pick on 1, 2, 3, 4 right here, you've got degree 4, that's bigger than 3, degree 4, bigger than 3, degree 5, bigger than 3, so those guys are fine. This one right here with a 1, that's degree 3, so that one's at least 3, which is okay. But you then start looking at, oh, wait, I've got 1, 2 edges that go in, but the third edge doesn't join to those other 3 guys, and that pulls the degree down, so that wouldn't work. Okay. Now, all of these vertices, let me check, have degree 3 or bigger, which means you actually have to check out where all the edges go. But with your 5 clique, here you need 5 edges with degree 4. Well, if we look at these degrees, what do we have? Degree 3, degree 3, degree 3, degree 4, that's okay, so 1. Degree 4, that's okay, that's 2 edges, vertices that work. Degree 5, that's okay. So we have 1, 2, 3 vertices that meet the minimum requirement of degree 4 or bigger. We don't have the extra 2 that you'd need for the 5 clique or the complete graph on 5 vertices. So bam, since you don't have 5 vertices that are at least degree 4, that means there is no complete graph on 5 vertices that's going to work. Or that's going to exist, I should say. Okay. So this one doesn't work. Only 3 vertices that are degree 4 or bigger. Oh, that was terrible. Let's change that symbol. Degree 4 or more. Now, that being said, like we saw with the K4, doesn't always work. But if you have this condition of not meeting the minimum degree requirement, that is a fast way of checking to see, nope, we don't have those cliques. And as soon as you have the first size clique that it doesn't work out, you then can say, hey, I can stop right there. None of the complete graphs that would be larger, that would have more vertices, would also work, because why? If we come down here to K6, you got to find 6 vertices with all of their degrees are 5 or bigger. Okay? Yes. So let me actually include that here. So one of the things that we have, if you have K, any subscript, that is always inside of when the subscript is bigger or not. They are, in fact, always nested, if you will. So any smaller complete graph is a subgraph of any complete graph on more vertices. And that's one of the reasons why when you check these different cliques, as soon as you get to one that doesn't exist in your graph, you can stop. You don't have to check any of the bigger ones. Okay? Kind of makes sense. A little bit makes sense. Now, actually finding it in the graph, some of these more complicated cliques, once you find your set of vertices that meet that minimum requirement of degrees, that can take a little bit of work. Question came in. Yeah, and that would, roughly speaking, be the logic of how you can do it. You can actually prove that result of the nested complete graphs, if you will, by using induction. And that, what you mentioned right there in the how you just add the extra vertex and insert all the edges to the previous ones, that's the induction step. Okay. All right, so I'm now going to throw this question to you. So the last wrap-up part of this question is, using this information that we just found, could we actually figure out, and I'm not going to read it out because if I read out the symbol, it'll totally give it away, but this question is currently up on poll everywhere. So here's the question. Can we figure out what the omega of G is? So I'm going to give you guys a sec to answer it. Actually, I'll share this with you and then unshare it just so you can see everything okay. So this is the question right here up on poll everywhere. It's exactly the same graph. I just took a copy of the one that's drawn out where we're working. And so the question here is, can we figure out what that omega of G is? And the only possibilities for your omega of G is it's a counting thing. So you can't have negative integers. It has to be an integer. And the maximum it could ever be is actually the same as the number of vertices in your graph, which is why your choices are 0 through 6. Okay. And I can give you that inequality of what the omega can be here in a sec. Okay. But take a second. It looks like many of you have found it, and I'm going to unshare this because it's the exact same graph. And so you can see the picture a little bigger. All right, it looks like most of you have guesses in. The last couple of you guys, make your guess quickly. We actually did all the work before. It is just interpreting what that symbol means. It looks like everybody except for 2 people have made a guess. I'm crossing my fingers that you guys are attempting guesses. 1 person. You can do it, last person, whoever you are. I should totally have paused the recording for this. Oh, well, it'll be silly if you guys ever watch them or listen to them. All right, so let us see what happened here. So the big thing is remembering what that symbol meant. Anybody remember what that symbol meant? It was, ooh, that's not, ooh, okay, yeah. I was interpreting it how you said that slightly different, but yeah, you could interpret it like that. So in this particular case, hopefully all of you were thinking that the answer is, can I write? Come pen. The answer is 4. So that would tell us what? You are grabbing this last one right here, which was the maximum clique that you got, Don't grab the edges. Grab the number of vertices that you use. And that's what that omega g is. It's literally just counting up the number of vertices in whatever your maximum clique was. And the reason it does that is because, remember, even though we did the symbols right here for the complete graph, it's really, in terms of the cliques, this really was a 4-clique. Sorry about that. Those letters all smeared together. That was attempting to be the word clique. And the 4 here just pulls the 4 from in front of that name right there. Okay? So there you go. Now, here's the inequality I was muttering about while you guys were figuring out that number. Because that omega g is dealing with the subgraph and specifically the number of vertices in your complete subgraph, the worst you could be is 0. Lies. The only way you could be 0 is if your graph didn't exist. In other words, there were no edges and there were no vertices. Okay? The best you could be, wow, that's, let us fix that. I have too many lines. The best you could be is that your graph itself was a complete graph. So the only time that this omega g is, this number is the same as the number of vertices in the given graph is if you actually have a complete graph, if this guy was a complete graph. The only way this is 0 is if you literally have no vertices or edges. Most of the time, this number right here is typically 3 or bigger. 2 will happen if you have edges, and to get 3, you have to have at least one that looks like a triangle. Okay. So that's this right here. Let me actually write this as a note. That way it doesn't get lost in the future. Now, all of this stuff was the background to the thing we care about, which are colorings. Okay? If you talk about a coloring, it is automatically referring to the vertices, which is why we talked about the vertices previously, okay, or just a second ago. So a coloring of a graph, also known as a K coloring, and the K here will actually tell you how many colors you used. So just like we had the 4-clique or the 3-clique or the 2-clique or the 1-clique or whatever, you can have a 3 coloring, and that would be you use 3 colors to color your graph. Okay. So the coloring is where you take the vertices of your graph, and you color each of the vertices, so you literally make them a different color, and we'll go in and make them different colors today, and probably the rest of this week we'll be dealing with colorings. We'll color each of these vertices in such a way that adjacent vertices have different colors. In other words, if you're traveling around your graph along your edges, when you leave one vertex that's, pick your favorite color, maybe it's, I don't know, black, like we normally draw them in, because we fill in the dots. And then we travel to the next vertex along the edge. The next vertex isn't allowed to be black. It has to be whatever other color you pick, okay? And if you only have one pen or pencil that you're using, typically people will do something like black and white, because black can be the filled-in circle for the vertex, and white can be the one where you don't fill in the vertex. Although if you're using colored paper, it would be black and whatever your colored paper was, okay? Unfortunately, that's only a 2 coloring, so then you have to be creative about the other guys. Okay. Now, one of the things that goes hand in hand with the vertex coloring, just like when we found the different cliques in the graph, we had some symbol that said what's the maximum or the largest clique that we could find in there. We have a similar thing here for coloring, except it has a number as opposed to a descriptive name, this being what's the maximum clique size, or just reading it off the symbol omega of G. Okay. So the thing that talks about your coloring, or how many colors you used, if you just say K coloring, that's any O coloring. And you can use what? You can use, if you want to meet this criteria, you can use every vertex is a different color, okay? So this K could be all the way up to the number of vertices in the graph, but it could also be less than that. Well, the chromatic number of a graph, and the symbol for chromatic number is this chi, this Greek letter, capital, looks like an X, but sort of script. Okay? This is the minimum or the fewest number of colors that can be used to color your vertices of a graph. Okay? So in terms of this guy, it turns out that there is a relationship. And the relationship goes as follows. Please make sure I'm still writing. Awesome. This guy here, when you have an actual graph in front of you, realistically, you're not going to, worst case scenario, the number of colors you used would be total number of vertices, And it turns out the smallest that it could ever be, and again, doesn't have to equal either of these, this is just a range. Turns out the smallest it could ever be is this max clique size, or this max clique size. And we'll look at that, why that works here in just a second, actually the very first example, which is how many colors do you have to use to color a complete graph, okay? Notice this is the number of vertices in a complete graph. So if there's something special with complete graphs, hint, hint, there totally is, you're going to have to worry about that inequality right there. Correct. One of the key things about the complete graph is it is where you've put in the most possible edges ever. And what that means is every single vertex is adjacent to all the other vertices in the graph. So I'm going to go ahead and actually just draw a couple of different complete graphs. We'll do like the first couple of them, and then we'll do a hypothesis of what the chromatic number is for complete graphs in general. Okay. So here, if we look at K2, which is probably way smaller than we needed to, you've got this guy. We look at K3, that's our one that looks like a triangle. And I'll go up to, how much room did I leave myself? Not a lot. So we'll do K4. We'll probably be fine with K4. And I'll let you guys tell me if you want to look at K5 as well before we get our guess for a chromatic number for these guys. So if we start looking at them, here with the first one, which is K2, what happens? You color one of the vertices, one color, and then the other vertex has to be a different color. Okay? So the chromatic number of this first guy, of K2, is 2. Now what happens when you're in the triangle? I'll color one vertex. Now what do I have to do with the other two vertices? You guys tell me. Can any of those other two vertices be that yellow color? This is why I love highlighters. Yep, I can't use yellow again, so you pick some other color. I don't have as many highlighters in the electronic form as I normally bring to this in person, so we'll have to be strategic about this sometime. So I picked a random color that's not yellow. I went ahead and colored it in, that's that blue color. Now, can that last vertex be the same? We already said it couldn't be yellow. Could it be that blue color? Now, anybody want to know the lazy way of coloring graphs? So right now we have, for this K3, we've got one vertex is colored yellow, we've got one vertex is colored blue. Anybody guess what the lazy color is for that third vertex? Yeah, just don't color in the last one. So we could call it, if you need to write down a color name, maybe it's black or clear if you wanted to. Or white if you'd actually made the vertices like little boxes that have nothing in there just because I have white in the background. So what this tells us is this tells us that the chromatic number here is 3. Now watch out. Note the chromatic number is not how many colors you used. It was what's the fewest number of colors possible that you can use. So when we were doing this in these two, at each stage we were trying to color another vertex the same color as a color we'd already used, but we were stymied. We couldn't because everybody was adjacent. Now let's see what would happen in K4. Suppose you pick some color. Maybe we pick yellow again because that's the first one. Can any of those other vertices be colored that same yellow color? Nope. Again, same issue. Pick another color. I went ahead and grabbed the blue. You pick another vertex, you color it in the blue. Can any of those remaining two vertices be colored with blue? Ah. Can we use that blue color? Nope, we're not allowed to use that blue color again, so we pick a different color. Green is the next one on my list here, so I'll use green. Maybe we color this vertex green. And can we use any of those previous 3 colors, the green, the blue, the yellow? We already said no to yellow and blue. So what do you think about green? Could we color that last vertex with the green? Don't overthink it. can that last vertex bottom right be colored green? Again, it can't because what? The green vertex we already have and the uncolored vertex are adjacent, which means they can't be the same color. Okay? So we can totally use another color to color in the sky, or we can just leave it uncolored, which is actually a perfectly fine thing to do. It happens all the time. So if we leave this uncolored because I'm being lazy, what would be the chromatic number of the complete graph on 4 vertices? Correct. Now, anybody have a guess what the chromatic number would be for any old complete graph? I did not mean to write it like that. You're right. It would totally be the number of vertices. So if we write it the way that I just wrote it, we'd put an N there at the bottom. Now, remember tie-in. This guy right here, your maximum clique size, what was it? It was the number of vertices of your largest complete subgraph. So why would this be your lower bound of your chromatic number? Because if you have a copy of the complete graph as a subgraph somewhere in your graph that you're trying to color, you're going to have to use N colors on that subgraph. Now, everybody else might use the same N colors, and that's when these two guys would be equal to each other. Or maybe you have something weird going on elsewhere that you have to use an extra color involved. But anytime you have a copy of one of the complete subgraphs, you're going to have this lower bound right here. That says, hey, we've got to use different colors on each of those vertices of that complete subgraph. Okay? So that would be the tie-in between these two guys. But it also gives you a formula in general. And that's something that's super useful. Okay? Questions make sense, kind of feeling okay-ish. The rest of the graphs are not complete graphs for the examples that I've got. All right, so I'm going to throw this question to you guys, but let us go back to that graph that we just looked at, and I activated it up and pull everywhere. So it's the same graph we looked at just a second ago, the one on 6 vertices that we found the maximum clique for. Anybody have a guess on how many different colors could be used to color this graph? Now, obviously, you could color it with 6 colors because there's 6 vertices. So let me scroll down here so you can actually see the graph again in the thing I'm sharing. But it is also up there and pull everywhere right now too. Okay? Now, what would you say with the inequality? The inequality said we have a complete subgraph right here on 4 vertices. So for sure, these 4 vertices are going to have to be colored different colors. The question is, if you're trying to find the chromatic number of this particular graph, you want to know, all right, well, on these additional 2 vertices over here, can I use the exact same colors that I used on the 4 that were inside of your complete subgraph or not? Okay, so let you guys think about that for just a second, and then we'll come back together and talk about it. And after we deal with that example, we'll go on with some other famous graphs and look at their chromatic numbers. And just as a side comment, while you guys are thinking about that question, the goal when you're looking for the omega of G, you're looking for the maximum clique size, so you're trying to get that number as high as possible. Whereas with the chromatic number, you're trying to use as few colors as possible because it's a minimum coloring that you're looking at. So for that one, you're trying to get the number as small as possible. But both of them can be numbers ranging between 0 up to the number of vertices of the graph. Although that inequality that you've got between omega of G and the chromatic number of the graph, there is a relation, an inequality there between them. All right, it looks like most of you have a guess. So instead of answering the question, what I'm going to do while you guys are finishing up your guesses, for the couple of you who haven't made a guess yet, is I'm going to go over how to make a coloring, okay? And then the rest of our examples are going to deal with this coloring too. So first thing that you would do is spot any cliques you have, and specifically you want to look for your maximum cliques. Okay, so here we already identified our maximum clique, so I'm not going to get rid of the highlighting even though I was really tempted to do so. Instead, I'm just not going to be able to use the yellow highlighter. Oh, sad day. I hope I have more highlighters. Ooh, there's more highlighters. All right, so here, what can we do? We can say, hey, maybe we highlight vertex. Yeah, maybe we won't do it that way. All right, so I'll just do bubbles. Maybe we go ahead and we color vertex 3 orange. Now we know that everybody in that maximum clique has to be colored something different because we just looked at what happens in a complete subgraph. So I'll just pick a couple of different colors, some of the ones that are somewhat near the top and easy to find, maybe a blue one. We'll see if that actually turns green. Oh, no, that stayed blue. Awesome. Maybe we pick trying to find ones that look distinctively different. Maybe a yellow one. Oh, that was not a good one to pick because I got it too big. Let's try this. Also not a good one because there's yellow highlighter. And let's see if we can't find something similar to green. I think I saw green up in here. All right. Oh, those are terrible colors, but at least they're all distinct from each other. Okay. It can be. So one of the things to do, one of the strategies to do is to start with the vertex of the highest degree. On this one here, I'm on purpose looking at the maximum clique, but if you aren't thinking cliques, that's totally fine, and starting with the vertex with the highest degree is definitely a strategy. In this case, it turned out to be one that was actually inside of the clique, so whether we did the clique first or the maximum degree vertex first, it actually didn't matter. Okay. Now, once we go ahead and do this, one of the things that we can do is actually, let's look at this guy with a maximum degree. I believe it's vertex 3 here. It looks like he's got degree 5. What does this mean? Well, with degree 5, this vertex 4 is adjacent to everybody else, so can we color any of our remaining 2 vertices that color green? What do you guys think? Is green allowed to be used again? Correct. So green is out off the table. Awesome, because I actually really hate that color green. Works for me. All right. So now, when we look over here at vertex 1 and vertex 6, what are we not allowed to do? We're not allowed to color either of them the same color as any vertex they're adjacent to. So notice they are adjacent to each other, so you're not going to be able to color them both the same color. So that being said, if we look at all the vertices that 1 is adjacent to, it's adjacent to 6, no help there because neither one are colored yet. Let's see. 6 can be blue. Yep, 6 can be blue because it is not adjacent to vertex 2, so let's go ahead and do that one. Let me find that sort of blue color we did before. And you said 1 could be orange? Yep, 1 could be orange. So 1 right here. At this moment in time, 1 is not allowed to be blue. It's adjacent to 2 blue vertices. It's also not allowed to be green because it's adjacent to vertex 4. It could be either orange or yellow. It actually could be any color you haven't used yet as well, but if you want a coloring that will get you to the chromatic number, you always try to color your vertices a color that's already been used unless you're forced not to. So this guy, if we're using colors already in play, has to be colored either orange or yellow, and it doesn't matter which. So let's go ahead and grab orange because that's the one you guys said. So that is one possible coloring of this graph. Now, if we look at what we just did, and I'm going to get back so I can draw in black here. If we look at what we just did, could we actually have colored this graph? Let me make it so you can see my cursor. Could we actually have colored this graph using fewer colors than what we just used? Is that humanly possible? Yeah, so we had a maximum clique of 4, which meant you had to have at least 4 colors involved because you had to have the 4 vertices in the clique be colored with 4 different colors. We didn't use any extra colors in those 4, so this is one of those cases where the clique and the size of the maximum clique and the chromatic number are exactly the same. That's pretty common. I don't want to give you exact percentage, but in terms of the graphs that we're going to see, it's really common. It's probably higher than 50% if this happens. Okay? That being said, if we had something other screwy that went on, there could have been a situation where we had some extra vertex. It didn't form, there weren't enough edges to form a new or a different complete subgraph, but the edges were connected in such a way that you'd have to pull out a new color. If you had to pull out a new color to do this, then this here, this number for the chromatic number would actually bump up. Now, that being said, is this the only way to color it? Absolutely not. You could color it in a bunch of different ways, but all of them, if they represented the fewest colors possible, would all be using 4 colors. You could use different 4 colors, but even if you use these exact same 4 colors, we could have colored things differently. Like we could have colored vertex 6 here yellow because 6 is not adjacent to vertex 5. Okay? We could have reordered where those 4 colors were. I mean, there's lots of different things that we could have done. Okay? So this is in a graph that's just a randomly drawn graph, what happened. So the rest, I don't want to say the rest of the examples, but probably the rest of the examples today are going to be famous graphs. I don't think we're going to get past my last famous graph in the time that we have left. So let's just say it. The rest of our examples today are going to be named graphs. So what I did in this section was twofold. One was to just get you a lot of different examples of graphs and coloring graphs, but one was also to give you a little bit of a survey of some of the famous graphs that are around. And the first several are relatively small graphs. Okay? So any questions before we move on to the next examples, which are all focused on finding colorings and chromatic numbers? All right, I am not seeing any new questions come in, but if you find them or are in the middle of typing them, definitely send them in and we will deal with them. Okay? So the first famous graph after the complete graph is dealing with somebody called the cycle graph. The name of this guy or the symbols that represent him is capital C for cycle and then N. So here's what they look like. And I'll actually give us a couple of different examples. The smallest cycle graph technically starts when you have N equals 3. So this guy would be, I really don't want to start with the N equals 3 one because it's sort of a special case. So let's start with the ones that are not special cases. So C4 looks like this guy, and I'm on purpose going to draw the vertices sort of as open circles. That way we can put the colors inside, and we'll see how that works in the future. This is also going to show you how you can color these guys if you don't actually have colors. So the 4 cycle looks like that. Notice you can think of the N as either the number of vertices or the number of edges in the cycle. It doesn't matter because when you think about when we were finding cycles and such in a graph, what happened, you started and stopped at the same place. So this is one of the few times where, unlike a path, the number of vertices and the number of edges are exactly the same. So if we looked at this guy and we wanted to look at the details of it, well, there's a couple of things that we can see. We can see here that the number of vertices is 4. If we wanted to write out the number of edges, but right now that really doesn't matter, that's also 4. So that just gives you the details of the graph itself. If you wanted to look at its maximum clique, anybody have a guess what the maximum clique would be in this guy? Yes, to those of you guys sending in. Remember, a 1 clique is if you have vertices. A 2 clique is if you have edges. We totally have edges, and a 3 clique is if you have a triangle. Notice we don't have any triangles, so our maximum clique or maximum clique in this situation is a 2 clique. Okay. Now, that moves us on to our chromatic number. If we're looking for a chromatic number, that is looking for the fewest number of colors possible to color our graph. Okay? So in that particular case, notice, if we use the inequality, we know that this chromatic number has to be some number that's at a minimum 2, but no more than 4. Why? Because you can't use more than 4 colors because you only have 4 vertices. And you're not going to use less than 2 because if you use less than 2, well, yeah, it's not going to work because of your subgraph, your complete subgraph on 2 vertices. So any guesses how we could color this guy with the fewest number of colors possible? In other words, an example that illustrates a coloring to give us the chromatic number. I realize I walked myself into that answer. So what do we want to do? If we colored this first one, and I'm going to go ahead and do this as an example in terms of if you don't actually have any instruments to write with that are colored. So for example, this first one up here, maybe you colored that vertex in so it's black, or whatever your color is of your pen, your pencil, or your electronic pen or pencil, whatever you're using. What happens? The 2 guys adjacent have to be a different color. And remember, I made these open circles to begin with, so we can let them be the same color as whatever your paper is. In my case, my electronic paper here is white, so we'll color these two guys white. And then this last is fourth vertex down here on the lower right-hand corner. What could it be colored if you want to use the fewest colors possible? And you guys already sent in some answers, and they are the general answers, what you guys sent in. We are going to build ourselves a formula, yeah. So it does, and let me go and draw the picture before I give you the firm yes, but you are totally on the right track there, okay? Because there's a special case for C3 that we've got to worry about. So in this particular case, yeah, you get to alternate, and you guys have already started picking up on what the pattern it is. So this is why don't jump too fast, because the thing that people want to say is, oh, the chromatic number is always going to be 2, and it's not. So the other guy, which is not a special case, suppose we look at the next cycle graph bigger, so this would be 5. So there's going to be 5 vertices. I attempt to draw it somewhat evenly spaced. Pretend those were straight lines. So here we've got 5 vertices, so a situation where you have an odd number of vertices. We also have 5 edges, so if you prefer to think of this in terms of edges, that's okay too, but not necessarily. Don't type thing. If you look at the maximum clique in this graph, notice it's still 2 because you still don't have a little triangular shape there. And so when we start looking at our chromatic number, well, we'd love for it to be 2. We still know it's going to be between 2 and 5, but notice what happens. So say we shade in this top guy, and I'm using black here, so that turned out to be a black vertex. And I'm just going to go around here clockwise. So the next vertex would need to be a different color. We're too lazy to do anything other than uncolored or white because we have white paper. And the next vertex around, what should we color this next vertex around? It can't still be uncolored, so what could we do? We could totally fill it in. And then the next vertex going around, well, we could be lazy and not fill it in or have it white or whatever the color is of your paper or electronic paper. And then when we get to this last guy right here, notice what happens. We can't fill it in and make it black like we did the other ones. What are we forced to do? Well, this one where my cursor is right next to it. What do we have to do with that guy? In other words, what color do we have to color it? You have to color it something different. Yeah. Now, if you actually do have something that you can use that is colorful, like for example, I can go in and highlight that guy yellow, you make it a new color. If, however, you don't have any way to recolor it, yes, one of the strategies that people do is something like that, where they hatch it. And then that's a way to get like gray or a third color, okay? Name for a graph that draws edges between all of the nodes with the same color. Yes, and we've got an example of that coming up. Our example is the reverse of that. It's kind of like dealing with a dual, and I'm totally blanking on the name. So I'm probably going to have to get that name to you next time or just post it online somewhere. So if you don't see it by Friday, feel free to remind me. Okay. All right, so where were we? Right. So this one here, what's the chromatic number going to turn out to be for the cycle on 5 vertices? Perfect. Now, so far what we've done is we looked at some examples. Well, we looked at 2 examples. N equals 4, N equals 5, so 4 vertices, 5 vertices, and it turns out this works for pretty much any cycle. If it's an odd cycle, it works just like C4. If it's an, I said that backwards, even cycle, C4, odd cycle works like C5. So if you want to do your chromatic number, did I write anything? Oh, I wrote it down at the very bottom here. So what you can actually say is, hey, 2, if N is even, and 3, if N is odd. Now, what did we say at the very beginning? We said that, I said K3, not K3, C3, so the cycle on 3 vertices is a little different. So in this blank right here, we're We're going to look at that guy. Oh, that is a good question. It's easier for me to read it if you actually use colors as opposed to patterns. I'm not going to lie, especially when you do it really tiny, patterns are extraordinarily difficult to distinguish between, especially if it's not yourself who's doing it, and also if it's something scanned. Scan quality will actually mess with being able to distinguish between the patterns. So if at all possible, it's definitely easier for me to read and grade if you are dealing with legitimate colors as opposed to some other patterns. Now that being said, let me show you with this next example how you can do it where if you don't have the colored pencils or highlighters or whatnot and you don't want to use patterns, there is an alternative way of dealing with it. Yes, and that's how to do that. So one of the standard ways is if you need to use more than 2 colors, technically you can use hatch marks for the third one, but typically if you use more than 2 colors and you don't have different actual marking instruments that can do real colors, you typically do numbers for the colors. So let me show you that with this next example. So C3 looks like this guy. Okay. Now, if we went and we did it with proper colors, you do something like maybe you color this guy yellow, maybe you color this guy blue, and what would have to happen, you'd have to use a third color for the last one. I won't use that third color maybe in the future. Now, what happens if you don't actually have the colors? You can buy those vertices, these sort of big bubbly vertices now. You can actually write color 1, color 2, and my circle there was too tiny, color 3. So that is another way of labeling your guys with numbers to represent your colors. Now, if you do this, one, I personally find it miserable to read. It is correct. If you don't have colors, this is perfectly fine to do. Do please give me a little legend to the side and be like, 1 is my way of representing whatever color 1 is. Maybe you actually give a name of a color like red or whatever color you decide, okay? Just to make sure that I know that you know what you're doing here. And then, of course, with this one, since there's only 3 colors, the other way that you could color this guy is what we talked about up on C5 up there, where you can actually bubble something in, so shade it totally in. This is something that people do in the chalkboard all the time, which would be you shade it in with a chalkboard, you leave it totally blank, and then you do the cross-hatching. If you put the numbers outside the vertices, it typically means something else. Because if you put them outside the vertices, it turns out to be the name of the vertices. Yeah, so watch out for that. One of the things that we'll see, and this will be more in Chapter 4, is we'll start dealing with the names of the vertices and edges, which we already have, but you'll also deal with things that are something attached to the vertices or the edges. We're getting a glimpse of that right now with the colors. So these guys are the colors attached to the vertices. So let me actually write down vertex numbers. And this is where it gets even more miserable. Suppose the name of your vertices were 1, 2, and 3. And then you need to color them, okay? It depends how big you write. Make it big enough so that somebody could read a number inside. And this is one of the reasons why people try not to use numbers unless they have to, okay? So if at all possible, I would recommend trying to get actual colors, or if you can't do colors and you only have 2 or 3 colors that you're dealing with, do it with the black and white shading. Most people normally have a pencil and a pen, and you can normally see the difference between those guys, so that gives you a couple of extra colors right there automatically. Where was I? Right, anyway, so C3, notice what C3 is going on here, okay? So this guy is a cycle that's different from all the other cycles. Here's how it's different. Number of vertices is 3, so that's as expected. Number of edges, 3, so that's as expected. Chromatic number, what ended up being the chromatic number here? 3, and was that as expected? Yeah, so that looked similar and matched with what we got when we had the other odd cycle, so that actually is exactly the same. And that tells us that down here for our formula, this works for all of our n's. We don't have to adjust it to make a special case for C3. Awesome, right? Now, here's the part that actually changes. What is the omega of C3? In other words, what's the maximum clique in C3? Now, why would I say that's different? Rephrase, different from the other ones. Yeah, so all the other ones had a maximum of 2, and this is because C3 is isomorphic to who? It's isomorphic to the complete graph on K3. So technically speaking, when you're talking about cyclographs, yes, C3 is an actual cyclograph, but if you want one that's a cyclograph that's also not some other type of graph, you can actually start thinking of these guys as really starting at n equals 4 if you prefer. Okay, but that's special, and it's special because that smallest cycle is in fact isomorphic to a complete graph, or is a complete graph. All right, that deals with the cyclographs. The next one that we have is somebody called the star graph, and we've actually used it. I think I told you the name once or twice, but it is something we've seen before, even if we didn't give you the exact name. So let me give you a couple cases, or a couple of the first. Technically, there's one smaller. You could technically do this guy for n equals 2, but normally here you're going to be looking at n equals 3, so I'm going to start off with n equals 3. So here is S3, and it looks like this. And then we'll put the details below. S4, and S4 looks like this. They're trying to be connected. And then we'll do S5 last. So you should see a pattern once you've got 3 things. Not always, but patterns don't get established until you have 3 things. Oh, so that is a way to think about it. So that's not how I think about it, but yes, in this case, you could actually say that n is the number of edges. In terms of describing your star, there's always one vertex in the middle, and that one vertex is adjacent to everybody else. So the degree of this one vertex in the middle is going to be the same as n. All the other vertices have degree 1. And I normally think of it as the n down here. The number of vertices is n plus 1. But yeah, you could think of it as number of edges because that works here too. Okay. So here are some of the details. Did I put these details up top? The cycle? I did not, but let me go ahead and put the details up here. N equals the number of vertices and the number of edges, and all the vertices are degree 2. So those are the descriptive details for the cycle. For the star, we can do something similar. For the descriptive details for the star, the number of vertices is going to be n plus 1. The number of edges, which we're not really going to care about right now, is going to be exactly n. And we're going to have one vertex, 1 degree n vertex, and everybody else is degree 1. And that's enough of a description that you could draw the graph from, okay? So when we start looking at this guy, yeah, we're going to do the same thing. We're going to look at the omega, and we're also going to look at the chromatic number. So if we look at this first guy, our number of vertices is 4. Our omega here, we've got vertices, we've got edges, and we don't have any triangles, so that's 2. And what did you guys say your guess was? You thought this one was 2? Okay. So let's see how we would do it. What vertex would you guys like to color in? Because if we think our chromatic number is 2, I can just use white and black for our vertices. Oh, the other thing, the one with the at the cycle. This thing. Because everything else we just wrote should have been. All right. One way to think about cycles is they look like polygons. If you draw them evenly spaced, they're the ones that look exactly like polygons. All right, so for the stars, so here we want to fill in the thing I like to do, and this actually refers back to what one of you said previously, which is starting with a vertex with the highest degree. The vertex in the middle is the one with the highest degree, so suppose you shade in the vertex in the middle black. Do we need to color any of the other vertices anything different than what they already are? And that is the lazy person's way of coloring that first graph. So, is that the fewest number of colors possible to color that graph? Yep, it totally is. So, our current guess, and we'll confirm this and see if it actually looks good for any of them, the current guess that you guys have is the chromatic number for the star graph for any n is, what did you guys say, 2? Okay. It actually gave a guess for the other one as well. And we'll confirm that. So if we look at this next one with S4, what happens? The number of vertices is 5, 4 plus 1. The omega is what? Well, definitely vertices and edges, so for sure it's at least 2. Does it have any triangles? Nope. Well, think about what a triangle is. You have to have what to get a triangle piece? You have to have at least 3 vertices of degree 2. Are we ever going to have at least 3 vertices of degree 2? No. So this one's just going to stop at 2. So yes, that one is true. Now, if we look at the chromatic number here, let's try to color it with as few colors as humanly possible. If we go ahead and color in the maximum degree vertex first, I'll color that one in. Do we need to color that second star graph anymore? We do not, so that one's done. Now, last one, we could color this one in. If we color in the maximum degree vertex there, remember we have 6 vertices, and our omega, or our maximum clique size, is, what is it, 2? Do we need to color in any of the other vertices other than just leaving them white as the lazy way of doing it? Or whatever color your background paper is. I guess you could think of it as clear. So no, you don't have to make any changes. So we use 2 colors, filled in or not filled in. So in this particular case, what happens, notice the hypothesis that we have right here. Since we have the majority of all these vertices are degree 1, what does that mean? That means all those degree 1 guys can be colored pretty much the same color, and then the one guy who's adjacent to all of them gets to be colored the second guy. Okay? And that is totally true with the star graph. Now, in your star graph, the smallest star graph, just to throw it out there, is S2. S2 is actually isomorphic to another type of graph called a path graph. Okay, that just didn't work with me. But this one here, it just doesn't look like. Okay, so the omega is the same guy, and the chromatic number you get just fine. So that's still okay. And I think we have enough time to look at least one example of the graph. We'll end with those guys, and we actually might end in another example depending on based on the time it currently is. Okay. So questions so far? Feeling comfortable so far? All right. So wheelgraph. Wheelgraph actually merges the last 2 types of graphs. Okay. So the wheelgraph looks like this. So for example, suppose you take a star graph and you pop a cycle around the outside guys. Roughly speaking, it's like merging it. Okay, so this is a wheelgraph. This is considered W4, 4 because 4 vertices. Okay. Now, next wheelgraph, W5, looks like this guy. 4 of those 5 vertices form a cycle. Okay. And then the middle vertex is adjacent to everybody else, and that forms your star in the middle. Okay. And let's do one more example. Wheelgraph on, or W6. This one will look like a pentagon around the outside. And then you've got 1 vertex in the middle, that's adjacent to everybody else. Okay? Now, for these guys, I'm going to start with the last two. So we have what? We have 5 vertices. And if we look for the max clique size, anybody spot a max clique size here? It's a little bit more complicated because it's a little bit more complicated graph now. So for K4, you're going to have to find something that has 4 vertices. Everybody has at least degree 3. All right, we've got that. And everybody needs to connect to everybody else. This guy actually does not have a copy of K4 in it. Like it's close, like this one's close, but those two don't connect. Does it have a triangle in it, though? What do you guys think? Oh, I've got a couple guesses for K3. Yeah, K3 does work. Got a triangle, so that one's 3 right there, no worries. So that means our chromatic number has to be somewhere between 3 to 5, so it's either going to be 3, 4, or 5. Hint, we don't want it to be 5, so we want it to be 3 if possible, okay? So what do you think with that guide? Do you think we could actually figure out how to color this with 3 colors, if at all possible? Well, first thing is color the inside one. So maybe we color that one yellow. And if we can do 3 colors, I can color everybody else just in shaded or unshaded. So maybe we grab the top left corner. The next one over here would need to not be yellow, so I'll leave it unshaded. Down here, I would need to shade it in. And then over there, I would need to have it still be unshaded. Okay? So notice what were we able to do? We did the same thing that we did on the cycle on the outside, and the inside one was some other color. Now, the question, of course, is can we get the same strategy over here? And when we start looking at W6, you say, all right, well, can I figure out what's going on here? And it turns out, just like in W5, the max clique size is still 3. You can see the 3 because you can spot a triangle. It's just checking to see if K4 is there or not. Okay. For this one, you can do something similar. You can maximum degree guy in the middle, and then you try to go around the outside, coloring it colored or uncolored. If we color the top one, we'll shade it in. Next one would be unshaded. Next one would be shaded. Next one would be unshaded. And the next one, what do we do with this last guy right here that has the arrow in front of it? You have to pick a new color, exactly. You can't use the yellow from the inside. You can't use any of the other 2 colors, so we have to go ahead and pick a new color. There's no way to get around it. And even though we did not have a subgraph that was a complete graph on 4 vertices, that's one of the ways you can force yourself to have a chromatic number that's bigger than your max clique size, or max clique order, to be more precise. Okay, so notice what we did. We merged what we would have done with a cycle and what we did with a star. And while we were thinking about that, I went ahead and wrote down the details for the wheel on 4 vertices. It actually is isomorphic to K4, so it has all the same details as K4. So we are totally out of time. So next time we'll start up here and we'll come up with a guess for what the chromatic number should be for an arbitrary wheel. Notice they have different chromatic numbers, so just like with the cycle, you're going to have, yeah, that's basically what's going to happen here. If you have an even cycle or an odd number of vertices, it will be 3, and if you have an odd cycle or an even number of vertices, it will be 4. That's it for today. If you got questions, I'll hang out for a few minutes, but we are all done.